Good morning, all of you. Today we are going back to chapter 1 Solid State, Electrical and Magnetic Properties of Solids. This topic is introduced this year in that chapter. This is newly introduced, so we are going to that topic. First is electrical properties in metals. So, conductors, semiconductors, and insulators. These are the three categories. Metals can be classified into three categories based on their electrical properties: conductors, semiconductors, or and insulators. Let's see what are these things. So, based on this electrical properties, solids are classified into three categories: insulators, insulators, semiconductors, semiconductors, and conductors. Their conductivity ranges from 10 to the power minus 20 to 10 to the power minus 10 ohm inverse meter inverse. For semiconductors, 10 to the power minus 6 to 10 to the power 4 ohm inverse meter inverse. It is a unit, ohm inverse meter inverse. And conductors, 10 to the power 4 to 10 to the power 7 ohm inverse meter inverse. Now, what is the cause of conductivity in the metal? That is due to electrons. Due to the presence of electrons only, metals are acting as good conductors. Now let's see the conduction in metals by band theory. Band theory. You consider the metal lithium. Electronic configuration is 1s2, 2s1. So in a metal piece, in a lithium metal piece, there are so many atoms. Metal atoms have atomic orbitals. Atomic orbitals form molecular orbitals. Molecular orbitals, which are so close in energy, together we call a band. Molecular orbitals, which are so close in energy as to form a band. If this band is partially filled, so you see so many lithium atoms, in this metal, so many lithium atoms. Now, 2s molecular orbital, 2s molecular orbital, you know the molecular orbital. Last year we learned 2s molecular orbital. Two S, 2s. So here, so many 2s molecular orbitals are there because so many atoms are there, so many molecules, so many 2s molecular orbitals. So in this 2s molecular orbital, see only one electron is there. So here one electron, here one electron, so here comes two electrons. So what happens here? This is the bonding molecular orbital and this is the anti-bonding molecular orbital. Anti-bonding molecular orbital, and there also this is empty. So many bonding molecular orbitals are there. So many anti-bonding molecular orbitals are there. Now here, these so many bonding molecular orbitals, so many anti-bonding molecular orbitals, if this band is partially filled, of course, so many bonding molecular orbitals are filled, but anti-bonding molecular orbitals are empty. We say this band means together this bonding molecular orbital and anti-bonding molecular orbital, which are so close in energy, bonding here bonding molecular orbitals and anti-bonding molecular orbitals, they are having close energy. I should not have drawn like this, like close by. So here close by energies, they form a band. So many bonding molecular orbitals and so many anti-bonding molecular orbitals together form. They are so close in energy, so they form a band. If this band is partially filled, you know that only bonding molecular orbitals are filled. So if these means so many are there, so many I can show like this. You see, only bonding molecular orbitals are filled. Bonding molecular orbitals are filled. Now, in this band means that includes all the orbitals, molecular orbitals, which are so close in energy. So, in this band, only bonding molecular orbitals are filled. Anti-bonding molecular orbitals, which are so close in energy to this bonding molecular orbital, they are empty. So what happens? Electrons can flow under an applied electric field. If this metal is kept in an applied electric field, electrons can flow. Why? Because there are gaps. If this we say if this band is partially filled, of course it is partially filled. Only bonding molecular orbitals are filled, anti-bonding molecular orbitals are empty. So if this band is partially filled, then what happens? Electrons can flow easily under an applied electric field. Oh, this is the case of lithium. Now, in beryllium, that anti-bonding molecular orbitals are also filled. This is also filled. I have drawn together BMO and ABMO together. That is, this band is completely filled, but it is overlapping with, its energy is overlapping with what? Its energy is overlapping with an unoccupied conduction band. If it overlaps with a higher energy unoccupied, we call it as conduction band. So filled ones, lower energy ones are called valence band. Higher energy unoccupied ones are called conduction band. So once again, if this band is partially filled or if it overlaps with a higher energy unoccupied conduction band, in both the cases electrons can flow. If it overlaps with what? Okay, if it overlaps with an unoccupied conduction band, 2p, 2p is empty. 2p is empty in the case of beryllium. Only 2s BMO and ABMO are filled. But its energy is overlapping with the unoccupied higher energy band, that is called conduction band. Then the electrons can flow easily under an applied electric field and the metal shows conductivity. So in this case, see, metal shows conductivity. So in the case of lithium, only Two SBMOs are filled. Their ABMOs are empty. BMO and ABMO, they are having almost close in energy, almost same energy. So together we say molecular orbitals which are so close in energy, together we say a band. So this is a band, this is a band, this is a band. Now this is called this 2p. 2p is called conduction band. 2p is called conduction band. Band formed by lower energy valence orbital. Lower energy valence orbital. Here, in the case of silicon, lower energy valence orbital. Band formed by lower energy valence orbital is called valence band. And the band formed by slightly higher energy valence orbital is called conduction band, is called conduction band. So here lower energy valence orbitals are called valence band, and higher energy band formed by slightly higher energy valence orbital are called conduction band. This conduction band is unoccupied. So in the case of lithium, this band is partially filled. This band is partially filled. In the case of beryllium, in the case of beryllium, this is overlapping with, this valence band is overlapping with a higher energy unoccupied conduction band. So in this cases, under an applied electric field, they show conductivity. So electrons can flow easily under an applied electric field and the metal shows conductivity. So lithium shows conductivity, beryllium shows conductivity. Now come to this portion. Now here there is a large gap between valence band and conduction band. So electrons from valence band cannot jump to this conduction band. So this will act as an insulator. But here, this gap is small. This gap is very small. This gap is very small. Suppose you heat this semi-metal, electrons will get energy and they can jump to the conduction band. Now, here, this is a semi-metal. Semi-metals are having the properties between metals and non-metals. Metals and non-metals. So, if the gap between, here, once again, if the gap between the filled valence band and the next unoccupied conduction band is very large, then electrons cannot jump to it. So, the substance behaves as an insulator. The large energy gap is called forbidden zone. Forbidden zone. So this is called forbidden zone. This is a one markation. What is a forbidden zone? The large energy gap between the valence band and conduction band is called forbidden zone. Now we are going to learn semiconductors here. If the gap between the valence band and the conduction band is very small, if the gap between the valence band and the conduction band is very small, then electrons can jump to it and show conductivity. Conductivity of a semiconductor increases with increase in temperature. When you increase the temperature, it will be getting heat energy. Since more and more electrons can jump to the conduction band, then we call it as it is a semiconductor or semi-metal. Example, silicon, germanium. By heating, the conductivity increases. Such conductors are called intrinsic semiconductors. Intrinsic semiconductor. Not only by heating, their conductivity can be increased by adding impurities to them. So now we are going to learn only this thing, that is semiconductors or semi-metals. By heating, By heating, if the conductivity can be increased, we call the semi-metals as intrinsic semiconductor. By doping, also you can increase the conductivity. Doping means we have already seen adding impurity. Doping means adding impurity. So here, by doping, if you are increasing the conductivity, then we call it as extrinsic semiconductor. Their conductivity can be increased by adding an appropriate amount of suitable impurity. This process is called doping. This introduces electronic defects in them. So by adding impurity, we say doping. So there are two types of the semiconductors, extrinsic semiconductors. First one is electron rich impurities. We are adding electron rich impurities, means silicon, we know 14th group, germanium 14th group. So valence shell contains 4 electrons. So when silicon is doped with 15th group, it can be doped with 13th group also. Now I am going to add electron rich impurities. Electron rich impurities. So silicon, last shell 4 electron. Next silicon, last shell 4 electron. Next silicon, last shell 4 electron. Next silicon, last shell 4 electrons. Silicon, so in a silicon solid semi metal, so here bonds are formed, covalent bonds are there. Covalent bonds are there. Now, when the silicon is doped with, means impurity, I am going to add an impurity. When the silicon is doped with arsenic, that is a 15th group, arsenic. So what happens? This is arsenic electron, arsenic electron. Arsenic has got 5 electrons. So one extra electron. Per atom, one extra electron is free. So 4 out of 5 electrons are used to make 4 covalent bonds with the silicon. The fifth extra electron is free. This one. The fifth extra electron is free. So this extra electron is responsible for the conductivity. The increased conductivity is due to these free electrons. If you add more and more arsenic, more and more free electrons will be there. So these free electrons can carry current, and we call it as N-type semiconductor. We call it as N-type semiconductor. N-type semiconductor. Why? Because the conductivity is due to electrons, negative charge. Electrons, negative charge. So N-type semiconductor. If you dope this silicon with a 13th group element, for example, boron, instead of this arsenic, if I am putting boron, then what will happen? Boron has got only 3 electrons in the valence shell. So 3 bonds will be formed with 3 bonds will be formed with silicon, and there is a gap. This gap is called electron hole. This gap is called electron hole, and we consider that the nature of that hole is positive. Now what happens? This is also a good conductor. How it becomes a good conductor? Now from the neighboring bond, one electron will be coming here. So the new hole will be generated here. Now from the neighboring bond, one electron will be entering here. So a new hole will be generated here. So what happens? When this electron goes here, from the neighboring bond, when one electron goes here, this will be full. That is, this will be full. That time, here is the hole. Here is the hole. New hole is developed here. Now, from this neighboring bond, one electron enters here. So, this will be full. This will be full. So, a new hole will be developed here. So holes are moving in this direction. Electrons are moving in this direction, holes are moving in this direction. The movement of holes is opposite to the movement of electrons. So there is conductivity. We say the conductivity is due to the holes. The conductivity is due to the holes. Holes are having positive charge. So we say conductivity is due to the holes, electron holes. So due to this positive charge, we say it is p-type semiconductor. It is p-type semiconductor. So the movement of holes in this way, movement of electrons just opposite to that. We have already given that negative charge in the previous case. So now we are using electron hole, which is considered as what? Positive in nature. So here the conductivity is due to electron hole or positive movement of positive charge. So we call it as p-type, positive p-type semiconductor. So n-type semiconductor, p-type semiconductor. In both the cases, what we have done? Doping. In the first case, silicon or germanium was doped with arsenic, that is of 15th group, or phosphorus, that is of 15th group. Now silicon or germanium is doped with 13th group, boron. So we have negative and positive. First one n-type semiconductor and second one p-type semiconductor. A combination of n-type and p-type semiconductors are used as rectifiers. A combination of n-type and p-type. N-type or p-type. You can write like this also. N-type and p-type. A combination of n-type and p-type semiconductors are used as rectifiers. Rectifiers means rectifier can convert AC to DC. AC to DC. Now, transistors are made by sandwiching one type of semiconductors between two layers of other type. So, you can consider this is p-type and the next is n-type and the next is p-type. So we call this transistor as PNP transistor. This is used to detect or amplify audio signals. So this is PNP transistor, or you can make NPN transistor. This is N and this is P and this is N. This is called NPN transistor. NPN transistor. So a combination of n-type and p-type semiconductors are used as rectifiers. So it can be this can be used as rectifiers. This can be used as transistors also. Transistors are made by sandwiching one type of semiconductor between two layers of other type, two layers of other type. See, one type between two layers of other type. Transistors are used to amplify audio signals, detect and amplify audio signals. So here we used silicon as the base substance, silicon or germanium, 14th group, 14th group. So many electronic things are made, mobiles, computers. So every time this to get this semiconductor, silicon and germanium, that is not easy to get. So what we did, a large variety of solid state materials are prepared by a combination of 13th group and 15th group. So we call it as 13-15 compound. 13-15 compounds. We call it as 13-15 we call it as 13-15 compounds. So only with the 14th group elements the things are not possible. So scientists made what they made by combining 13th, 15th group compound means elements, and they simulated an average valency 4, average valency 4 to make an average valency 4 similar to that silicon or germanium. So a large variety of solid state materials are prepared by the combination of 13th groups and 15th groups to simulate an average valency 4. For example, gallium arsenide or aluminium phosphide or indium stibide. So 13th group, 15th group. So this is 13th group, that is 15th group. So to simulate an average valency 4, to simulate an average valency 4, 13th group elements are mixed with 15th group elements. We call them 13-15 compounds. Or 12-16 compounds, then also you can simulate an average valency 4. To simulate an average valency 4, elements of group 12 and group 16 are combined. For example, Zn sulfide or cadmium sulfide. But these are not perfectly covalent compounds. So these are called 12-16 compounds. We say compounds only, 12-16 compounds. This is to simulate an average valency 4. Next, magnetic properties. Magnetic properties of solids. When we learn electrical properties, solids are classified into 3: insulators, semiconductors, and conductors. Here the solids are classified into 5. That is paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic. Each electron in an atom behaves like a tiny magnet. Magnetic moment originates from two types of motion. One is orbital motion around the nucleus and one is spin motion about its own axis. Now let's see what is paramagnetic substances. Substances which are weakly attracted by the magnetic field is called paramagnetic substances. They lose their magnetism in the absence of the magnetic field. Paramagnetism is due to one or more unpaired electrons. So here, unpaired electrons will be there. These are magnetized in the same direction of the magnetic field applied. So suppose this is the applied magnetic field, north, south. And suppose you are putting a safety pin over there. Now safety pin will act as a magnet. They lose their magnetism in the absence of this magnetic field. They lose their magnetism. The safety pin is kept over here. So the safety pin, if you are taking out the safety pin, now the safety pin cannot act as a magnet. When the safety pin acts as a magnet, Then another safety pin can be. Then another safety pin can be kept. Another safety pin can be kept. So they lose their magnetism. This fellow loses their magnetism when the magnetic field is removed. Example, Cu2 plus, Fe3 plus, etc. So paramagnetism, that is a weak magnetism, paramagnetism is due to the unpaired electrons. Next, diamagnetism. Diamagnetic substances are weakly repelled by a magnetic field. For example, NaCl or H2O. It is shown by those substances in which all electrons are paired. So no unpaired electrons. All electrons are paired. So no unpaired electrons. And there are no unpaired electrons. Pairing cancels their magnetic moments. These they are magnetized in the opposite direction of the applied magnetic field. So there is a magnetic field, applied magnetic field, north, south, direction is towards the south, and the one we are keeping here, they are magnetized in the opposite direction. So they are weakly repelled by the magnetic field. Next, ferromagnetism. Ferromagnetism means they are very strongly attracted by the magnetic field. They can be permanently magnetized. You know that some blade which is kept in the magnetic field for longer time, and after the removal from the magnetic field also the blade acts as a magnet. So they can be permanently magnetized. Actually, in a solid state material, metal ions are grouped together. Metal ions are grouped together and we call them as domains. We call them as domains. D domains. Domains. We call them as domains. Small regions called domains. Each domain acts as a tiny magnet. In unmagnetized piece, these domains are randomly oriented. They are randomly oriented and their magnetic moments cancel each other. Their magnetic moments cancel each other. In unmagnetized piece, these domains are randomly or oriented and their magnetic moments are cancelled. When the substance is placed in a magnetic field, so here this is 0. When the substance is placed in a magnetic field, now what happens? All the domains get oriented in the direction of the applied magnetic field. So all these are oriented. Now all these are oriented in the same direction. In the same direction. This ordering persists even when the magnetic field is removed and it acts as a permanent magnet. Now I cannot write this as 0. There is magnetic moment. So this ordering persists. So you can show it like this. Now it acts as a permanent magnet. Now next is antiferromagnetism. In antiferromagnetism, in this case, in the presence of a magnetic field, the domains are oppositely oriented like this. The domains are oppositely oriented and cancel out each other. and cancel out each other's magnetic moment. So, see, this is a schematic alignment. So, in this case, in the presence of a magnetic field, domains are oppositely oriented and cancel out each other's magnetic moment. Example is M and O. And the last one is ferrimagnetism. In the ferrimagnetism, it is observed when the magnetic moments of domains are aligned in parallel and anti-parallel. So 1, 2, 3, 4, 5, 6. They are oriented, they are aligned in parallel and anti-parallel. See, parallel and anti-parallel directions in unequal numbers. In the presence of a magnetic field, they are weakly attracted by the magnet. Example is Fe3O4. So they are in unequal number. They are in unequal number. Domains are aligned in presence of a magnetic field. The domains are aligned in parallel and anti-parallel direction in unequal numbers. So we call them ferrimagnet. Thank you.